Hey guys, in this video we are trying to kind of sum up all of the experimental work that we've done this week, all the investigations where we have been trying to model an ideal gas. And the idea for modeling an ideal gas would be mainly to try to get a better perspective of how the different measurable variables of the gas relate to each other. Because if we can do this, then we can see, maybe how the gas can become useful. And that's kind of our next step, is to use that. But in this video, we're going to try to put together all the relationships that we've used this week. And a few of the main objectives of this video will be to come up with a full sort of idea of the ideal gas, both conceptually and mathematically. So I collected this data for pressure versus volume, and I did it in liters instead of meters cubed, just to kind of get an idea of the shapes. And we can see here on the left that we get this very nice power function that the independent variable is raised to pretty much -1, which is great. So this, if we write out this function, we have y equals 1039 over x. And then obviously y and x are, the y variable is pressure, and the x variable would be volume. Now that 1039, then the significance of that number may or may not be useful, because we have pascals versus liters, and commonly for us in physics, the volume is going to be in cubic meters instead. So that significance of that number may not be useful. To test if you were on a test and you wanted to verify that the power function was the correct, that truly is an inverse function, you could linearize the graph by graphing pressure versus 1 over volume. And when you see there, you get a very nice linear shape. So that sort of almost helps you verify that that is in fact an inverse relationship. In addition to that, when you look at it this way, we can get maybe some more information out of the slope that we may not have been able to get before. But this is important just to kind of look at these two relationships and think about what's happening now when you change the volume. So every time you made the volume smaller or larger, in the simulation that I used, I changed the volume and I tried to hold the number of particles constant by not allowing any more particles into or out of the system. And I also try to hold the temperature constant. Now this is a very important conceptual notion that we have to think about, is when you push the volume to make it smaller, so you make the container smaller, the gas particles are obviously going to collide with the walls of the container more often. And as we discussed in our our board meeting, that meant that the pressure would increase because there were more collisions with the container walls, hence more force per unit area and therefore a greater pressure. What's also interesting about that is that because they're colliding more often, there is going to be an increase in the speed of the particles if there is not some other way to hold the speed constant. And we also kind of discussed in our board meetings that by changing the velocity of the particles, somehow the temperature registers as a higher number or a lower number, depending on if you see the particles are speeding up or slowing down. And that's important because we've kind of made this link now that by increasing the average speed of the particles, the temperature seems to increase, and that is resulting in an increase in pressure somehow, although they're happening all at the same time. So in order to hold the temperature constant, if you didn't select to hold it constant, you couldn't really do this test very well, because what would end up happening is you would have multiple variables changing at the same time, and you'd have to find another way mathematically to relate all of those variables. If you look on the simulator and you try to do the exact replicate the experiment that I did by holding the temperature constant, you will notice that every time the volume is adjusted, the pressure changes And then at the very bottom, underneath the container, some ice shows up. And this ice is trying to remove heat from the system. And by removing heat from the system, the result is that the molecule's average speed decrease. So immediately, as soon as you change the volume of the container, you saw that the temperature increased suddenly. And then when the ice showed up on the outside of the container, it removed some heat from the system, thereby decreasing the average kinetic energy or average speed of the molecules, and thereby decreasing the temperature to hold it constant. So what's interesting about this, and this is going to become very, very important when we get to looking at different engine cycles and how the different states of the engine change from one pressure to another, or one volume to another, or one temperature to another, there has to be some consideration of this idea of heat. And we kind of started to mention it in class, that there's an interesting relationship between the heat and the temperature, but they're not the same thing. And so we have to kind of investigate that a little more, and we'll look at this. The main sort of point about what I just discussed is that in order to hold the temperature constant in this experiment, where the volume is decreasing per trial, thereby increasing the pressure, heat has to be removed from the system. In other words, we somehow have to remove energy to keep the molecules from moving faster because of their more frequent collisions with the walls. And so in the next slide, I collected some completely separate data from this that you see here to kind of get a better perspective of, realistically, how can we relate all these variables to each other. So let's move on to the next slide. Okay, so in this data, you can see I had to split the table to fit it here. I measured the length change of the sliding chamber, and I kept the area constant. That untitled column is the area, and I did it 1 nanometer by 1 nanometer, and the length was measured in nanometers. And there you can see I've tried to convert the length from nanometers to meters, and then I multiplied the length by the area to get the volume of the container in meters cubed. But I should get the same relationship. I was just trying to keep the units very specifically fixed with volume with meters cubed, instead of just using the length analog of that. So that's kind of what that all means. Very, very small volume, of course, in a very small chamber. I then took the inverse of the volume because, as you remember from the previous graphs, I wanted to look at the relationship between volume and pressure, and the inverse of volume and pressure. And there you can see I measured pressure in atmospheres and then converted to pascals. Remember that conversion is that in 1 atmosphere I have 100,001 about pascals. And so those are all the conversions. And then I had the temperature values, which I tried to hold constant. You can see one of them, the third data point, is 301, but it's pretty much constant, right? And I maintained that by removing heat from the system, or the simulator did for me. I kept the number of particles kind of low because I didn't want the chamber to explode when it got to a small enough volume where the pressure was pretty high. So I kept that low. And so the number of moles, which is an extremely small number of moles, was because I had a small number of particles. Now it's worth us taking a second to look at how to convert from the number of particles, which we use uppercase N, into the number of moles, which we use lowercase n. And we know that a mole is just like saying a dozen of something. Obviously not the same number, but it's the same concept. So if I have a dozen rolls, how many rolls do I have? Here we have how many moles, so how many dozen particles do I have if I have this number of exact particles. So we would take the number of particles, n, and divide that by Avogadro's number, which is provided for you on many standard AP given sheets and other tests. So we would take, in this case, 177 particles and divide that by 6.023 times 10 to the 23rd, which is Avogadro's number, and that should give me the number of moles. So very small number of moles here, but held constant nonetheless. What I was moving towards doing was trying to find out if pressure, volume, and temperature are proportional to each other. And so in this case here, what I'm going to see is, well, what I saw before is pressure is proportional to 1 over the volume. I also saw that pressure is proportional to the temperature, which I did not review in the video, but we did in our discussions in class already. And we also saw that pressure is directly proportional to the number of moles or number of particles. And so these three relationships we have here, if we were to create a compound relationship, we would have pressure is proportional to number of moles times the temperature divided by the volume. And remember, this compound proportion says that if I hold any one of those constants, so cover that particular variable with your finger, or other two variables with your finger, does the one that's exposed still show the same relationship of the original proportion? And it does. So we have this relationship here. Pressure is proportional to the product of the number of moles times the temperature divided by the volume of the container. Now I want to see if this is in fact an equation, so a model that can actually be, used to predict numbers that we didn't measure, or if there are other variables missing. You might think, well, maybe density's in there somewhere, maybe there's some other things in here, and maybe we need to consider those. So what I decided to do, if you kind of remember what we've done in multiple other experiments, is try to graph the pressure as a function of that, number there, Nt over V, and see if I get a direct relationship. If I do, that means that those two, that quotient on the right and on the left, the pressure, those are always changing by the same amount. So they directly relate to each other. They're linearly related, and then that would mean that I either have a constant that is in this equation, or perhaps a constant slope that contains other variables in it. And so if you know the ideal gas law, you may be already kind of seeing what's happening here. So what I did on this data table here is, you can see I have the n times t values, and then I have the n times t divided by v, or n times t times the 1 of the volume column. And these are all corresponding measurements, so they were all taken at the same time, which is vital to doing this. So I'm going to go to the next slide here, and we're going to graph those and take a look at what we find. Okay, so here we have pressure versus number of moles times temperature over volume. So on my independent axis, I have that chunk of things, mole kelvins per meter cubed, and on the dependent axis, I have pressure in pascals. And I get a nice linear shape with a slope of 6.775 or 7775 plus some y-intercept value. So let's rewrite this function with the variables in question here. So we have this y equals mx plus b relationship. The y is, of course, pressure. The m is 6.78. I'll make it that. And the x is going to be nt divided by v plus some initial pressure value over here. So that's our function that we have so far. This p0 value is most likely some error or something else, because let's try to think about that. We'll consider if it maybe isn't error. If I have a 0 plugged in for x, I should have a p0 value of what it says there, 4,690.6 pascals. It would be interesting to figure out what that means, what that initial pressure is, and we will discuss that a little bit more in class, but maybe you can come up with some ideas yourself. If we make any one of those values 0 over there, they all become 0, and then should I have a pressure value? Think about that. We'll discuss that in class coming up. The 6.78, interesting. You probably know this from chemistry. You've known probably all along what's happening here is that if I write this as P equals this number, so I'm going to just put this this way. I'm going to move the V over just to put it in a form that people always see. I have this let's round it even to 6.8 NT. Okay, you see here the sort of the Pivnert thing that everybody always calls it. This 6.8 is actually a constant. We're going to call it the ideal gas constant. Now you may be thinking, well, it's not 6.8. What I always learned was that it was 8.314 or something to that effect, depending on what units you were using. And so this is interesting. This is experimental error most likely. This is why I would say that P0 value kind of maybe provides us some indication of error, and the 6.8 is close. 7 is, pretty close to that 8.314, and that's the R. This is that ideal gas constant R. Here, this experimental value for R that we have is not 8.314 joules per mole Kelvin. Okay. It is 6.8 joules per mole Kelvin, which is an experimental value and an interesting thing to kind of analyze here. Let's flip to the next slide here and take a look at what this joules per mole Kelvin means, or what it is, just to kind of get a perspective of what's happening here. Okay, so we have this joules per mole Kelvin, and the joule is a Newton times a meter over a mole here times Kelvin. So what we could look at this as being is a Newton times a meter is a joule, which we also have defined as work. So it's the amount of energy per mole of substance per Kelvin, per change in temperature. So keep that in mind. I'm not going to go into it in more detail than that, but to think about the amount of energy per mole Kelvin. What does that essentially mean? So for every, let's say we keep the moles constant, for every temperature we increase, what does that mean about the number of joules? This sort of set value of 8.314 joules per mole Kelvin, how is this going to play into, as you think about joules being a measure of work, how work is going to be able to be done by the gas or on the gas as different things change about it. And this is a very interesting sort of concept. Very last thing we want to discuss now is something that I find very helpful in verifying. We got an R equals 6.8 joules per mole Kelvin, and I want to see if we can look at this from what's called the Boltzmann Constant perspective. So let's pull up that data again that we collected and take a look at what I mean by this. You may not know the Boltzmann Constant yet, and I'll explain what that is in a second. Okay, so we got our data back here. This is that same data I used to graph the relationship we just saw, pressure versus number of moles times temperature over volume, and we saw that we got this sort of constant, which we described as R equaling 6.8. We know that to be a little bit different than what we actually sort of standardly know it as. So let's look here at this. What if we wanted to do, instead of so we have pressure is proportional to number of moles times temperature over volume, we can see that the shape of the relationship is still going to be the same if I did pressure as proportional to number of particles, the uppercase N, times temperature per unit of volume. We should still get a direct relationship, right? Because the number of particles, the number of moles is directly related by Avogadro's number, so it should be roughly the same thing. But obviously we're not going to get the same value, the same number. So I graphed this P versus uppercase N T over V, or number of particles versus temperature, or number of particles times temperature over volume rather than number of moles. And let's see what the graph looks like. So there it is, pressure versus number of particles times temperature over volume. You can see there we get this y equals 1 times 10 to the negative 23rd x plus that same initial pressure value. Very, pretty nice fit there. And what's even better for me, knowing something secret here that I'm going to show you in a second, is that I know that this is actually maybe not as much error as I thought, maybe some. So I have pressure is equal to 1 times 10 to the negative 23rd times number of molecules times temperature all over volume. So before we would say this is P equals R little nt over V. Now we have P equals something times uppercase NT over V. Instead now of having number of moles, we have number of molecules, and now it relates by what we call the Boltzmann constant, Kb. So R is going to be this equivalent to this Kb value, and the Kb value is this. So when you write the ideal gas law, and this is very important for physics, not as much so in chemistry in high school, when we write the ideal gas law using a number of moles in the relationship, then we would use the R value. But when we write this ideal gas law using the number of particles in the gas, we use the Boltzmann constant. And if you look up the standard value for the Boltzmann constant, which is pretty cool, is it's 1.38 times 10 to the negative 23rd. And that's really close. I mean, we have 1 times 10 to the negative 23rd, and that's pretty good. So it's showing here that there is this standard relationship. The Boltzmann constant has a whole string of units. I think it's a meter squared kilogram per second squared Kelvin. So it's a little, it should look like meters squared, or kg meter squared over second squared Kelvin. And the units, we'll look at that in a little bit with the ideal gas law as well, kind of what that might mean is as the gas changes. So we sort of take-homes for this little video lecture are a few different things. Remember, we're looking at the relationships between the pressure, the volume, the temperature of the gas, and the number of moles or number of particles of the gas. If we want to relate all three together, pressure, temperature, volume, in terms of number of moles, we need to use the R, the 8.314 joules per mole Kelvin. And if we want to relate the pressure, temperature, and volume in terms of number of molecules in the gas, we need to relate it using the Boltzmann constant. We're going to get into those a little bit more as we sort of investigate thermodynamics. Big take home here as well is that we can say pressure, temperature, and volume are described as state variables. And we mentioned that in one of our board meetings. These state variables describe the state that the gas is in at an instant. And it can be described in terms of all those three variables and others as well that we'll add to. And then we're going to look at, really focus on this week upcoming, the change in the state of the gas. This is a big one from this lecture if you think about it. When we change the state of the gas from being one volume, say a larger volume, to a smaller volume, what changed? Well, the pressure changed, so that state variable of the gas changed. And the temperature, if we didn't hold it constant, then the temperature would have shifted as well. And so the gas would have been in a different state now. We're not talking about a different phase, per se, but a different state, a different pressure, a different volume, a different temperature. If we try to hold the temperature constant, if that is our desire, then changing the volume will change the pressure, and we will have to remove heat from the system. This is going to become our next sort of big undertaking with thermodynamics, is to try to understand how do these conversions, these processes, how do we change the state of the gas in different ways by holding various things constant. What if we wanted to hold the volume constant and only change the temperature? What would we have to do to the system, right? Think about that for a sec. So hopefully you paused the video and thought about that. As you change the temperature and try to see how it relates, how the pressure relates to that, how that depends, you have to hold the volume constant. That means you had to have added some heat to the system. And some of you kind of already started to figure that out on the little simulator that caused the particle speed to change, and therefore the pressure changed. So when we look at these different processes, what are the processes? It can be changing the temperature of the gas, see how the pressure changes. Changing the volume of the gas to see how the pressure changes. and then maybe changing the number of particles of the gas to see how the pressure changes. All three of those relationships relate to one another, and all three of them require that you hold other variables constant. Holding the number of particles constant is usually not that difficult, but holding the temperature of the volume constant requires some other sorts of changes. What if we wanted to look at the relationship between the volume and the temperature, perhaps? That would require holding the pressure constant. And how would you do that, right? So we're going to take a look at these different processes. So right now you should hopefully be able to describe the state of a gas. And after that, we will look at what's going to happen in terms of heat changes and all these other things. And what we're basically going to do is start constructing the laws of thermodynamics to help explain how these relationships between these different states of the gas occur and what they can be used for to sort of apply this knowledge to help human beings do things and get things moved. Very last statement here will hopefully help you with some of these post-lab questions, and I'll just flip to a new slide, is that if I have the gas in state A and I want to move it to state B, think about what can be constant always. Usually these three things are going to be constant, and these two things are going to be constant, and other things might be as well. So you'd have a pressure measurement here at A, a volume measurement here at A, and a temperature measurement here at A. These are just listed, and they're going to be a pressure measurement at B, a volume measurement at B, and a temperature measurement at B. So if we write the ideal gas law for this, P times VA over TA, that equals NR. And then over here on the right, we have PB times VB over TB. That also equals N over R. So by the transitive property, if the number of moles of the gas is not changing, even if it is, you just have the number of moles on the other side, or the number of particles, that the two states relate by this ideal gas constant, and hence allow you to solve a lot of problems by this kind of symmetry in a way. So hopefully you got something out of this video. You can put things together. In your lab notebook, you should construct a consensus of the information that we've kind of put together over a week of investigating these different things about gases in these ideal situations. So hopefully that helps. Please use some of the post-lab questions to help structure your sort of closing thoughts about the investigations of the state variables. And see you in class.